process can be converted into some sort of unit conversion probably. And we'll talk about how to take measurements, how to take accurate measurements, where we start estimating and things like that, and some of the basic units that we're going to be discussing. Before we get started, are there any questions on anything we talked about last week? We really only discussed kind of a math review, and we'll review that more as we actually start applying some of those. Yeah. Tyler? It was Tyler, right? Was it Tyler?
Yeah.
Okay.
I was looking for the solution, like on the modules for the slides that you have. For
I posted them this morning for the lecture. So if you look now, it should say math concepts, and then it'll have one right below it that says completed. And then I posted one of the lectures, right? Because we did one in lecture and then one in lab. Let me know if you see it. Do you guys see it there? Okay, yeah. So that'll have all the the slides. I post them kind of as we complete them, but obviously the fastest way to get it is to be in lecture doing that. But I know it's useful to go back and look, especially if it's lectures feels like it's going fast. And also, if things are going fast, don't hesitate to ask me to slow down. All right, and just some reminders. So the first problem set I posted last week, that'll be due this Friday. Again, that's a soft deadline. If you don't get it done by then, that's fine. You can still turn it in up until the first close date, but these are good guidelines. Stay on track for the course, right? If you keep postponing it, then all of a sudden you have a week and 5 problem sets and 5 labs to do. That'll be too much work to do, complete in a week. Okay, and then the lab 1 is also posted on Canvas. Like I said, I'll be giving you guys all the lab manuals that you'll be using for the semester. So this first one it's kind of a long lab, but so you're probably not going to finish all of it, but just get as far as you can. Just kind of get you familiar with basic lab techniques. And then again, you're going to be submitting those online, scanning. For today's lab, you can either write the answers on a separate sheet of paper and follow along on your tablet, or print them before you come. I'll try and have some extra copies printed, but the printing can be kind of slow here. So you just follow along, and then you'll submit your answers separately. But you can use your tablet or computer. The only thing is, if you're doing that, just be careful. If you're working with anything that you could spill or burn your laptop or iPads with, you don't want to do that, because that can be expensive. Especially once you start dealing with water hoses. I've had some people, they're working in the fume hood and they have the water hose hooked up, and the water hose pops off. It just starts spraying water everywhere, and then if your iPad or laptop's just sitting in there, it'll sit in a pool of about an inch of water really quick. Okay, so we'll start talking about measurements and unit conversions. All right, so we use what's called SI units, which are standardized units. And so these are used to measure very fundamental dimensions that we look at when we're looking at chemistry, physics, or any of the other natural sciences. And so usually we're talking about mass, length, time, and every other unit can be derived from some sort of combination of those three. And so if we have all these different units, and scientists are working all around the world, and they're all verifying each other's experimental results or conducting new experiments, they need some standardized way to make sure that they're measuring the same thing that other scientists are using. And so the SI system is a standardized system of measurement, and we'll talk a little bit about those units. And pretty much everything, like I said, that if you go into physics or anything, the SI units are used in all of the natural sciences. And they have a standard way to determine what each of these things are. And those methods of determining what a standard unit is are changing as instrumentation gets better, and we get better and better definitions of things as well. Okay, am I good to go on to the next slide? Just kind of just don't want to leave anyone copying, right? So what are some of the standardized units? Well, for a unit of length, the standardized unit is a meter. Does anyone know what the symbol for meter is? Yep, lowercase m, right? So that's the symbol. Whenever you see that after a number, that gives it a unit or a dimension, right? So sometimes I'll use unit and dimension interchangeably. So those can be used interchangeably. Dimension, interchangeable with units. And so when we talk about unit conversions, sometimes I'll also use the term dimensional analysis, which is just going between different units, going between different dimensions. The standardized unit for a unit of mass is a kilogram, right? And so a kilogram is represented by a lowercase k and then g, so that's kilogram. Seconds are a standardized unit for time, and that's just a lowercase s. Temperature, we use the temperature scale of Kelvin. So we use the temperature scale of Kelvin instead of Fahrenheit or Celsius because Kelvin is an absolute scale. We find that temperature is really kind of related to how fast molecules are moving or atoms are moving or vibrating. And so the temperature scale of Kelvin is just when things stop moving, that's when we define a temperature of 0, right? So it's not actually a real temperature that we can ever reach. We can get really close, we can't actually reach it. And so that gives us an absolute temperature scale. And so that's in units of uppercase K. The amount of a substance, so you guys may have seen this in chemistry classes you've taken before or heard of the term, is called a mole, right? So, and we usually just represent that with an MOL. Sometimes people will write MOLE for mole. It's used interchangeably. And these are kind of the important units that we'll be using here, right? So when we think about, how do these units combine? Well, you can form derived units from these standardized units, right? So these standardized units, you can have a combination of them, and that'll give us a unit for a force, for example. So a force is a kilogram meter per second squared. And then you have other units, an ampere, which is an uppercase A, that measures electrical current, how much current is moving through, or how fast the charge is moving. And then intensity of light, that's a candela, is represented by CD, but these are not so important. But once we talk about more abstract ideas like current and luminosity and stuff like that, we need also different standardized units. But if you go far enough into physics, you'll find that an ampere is really still a combination of some of the other seconds, length, and mass usually as well. Okay. Am I good to go on? I see some people still writing. I'll let you guys finish writing. So I mentioned before that you usually have some standardized way of determining what these are. So for example, a meter, it used to be defined as, 1/millionth the diameter of Earth. That's how we defined a meter before. But as, kind of science progresses, we have more accurate ways to measure these things, right? So now the standard unit is measured by how far light travels in around 1/300 millionth of a second, right? So you say, well, that doesn't seem, as useful. It seems a little more convoluted. Well, the reason it changes is because we can measure that much more accurately now than we could in the past, right? So a lot of people dedicate large amounts of their time and careers into making different measurements more and more accurate, right? So the most accurate measurement we have is the magnetic moment of an electron, and it's something that every year, people, spend, millions of dollars and, hundreds of thousands of hours trying to add one more decimal place to what that measurement actually is, right? So how fast or how far light travels in 1/300 millionth of a second is a lot more accurate than 1/1 millionth of the Earth's diameter, right? Because it's a much more accurate measurement. Seconds, it used to be measured as, a fraction of the time it takes for the Earth to rotate around the sun, and then also, how long it takes for the sun to, make its trip around the sky. But now the way we measure a second is by looking at a cesium atom, right? So if we look at the periodic table over there, we'll become very familiar with it. One of the elements up there is called cesium, and its nucleus can undergo a little transition, right? And when this nucleus undergoes a transition, we get a signal from it, and how frequently it's transitioning is really, really well defined, meaning that it happens at a very constant time interval. And so we can measure a second to a much more accurate decimal place by defining a second the number of transitions we get from this cesium atom, right? And so, well, the more accurate our measurements get, the more refined our experiments get, right? So if you're looking at something of interest, right, let's say it's a fraction of a day, right? You want to define a second that way. And that's as accurate as you can measure a second. Well, what about processes that happen much faster than that, for example? So if we're looking at something in biology, right, like cellular respiration or something, those processes happen on very, very fast time scales, typically. And so you can't measure that if you don't know, how many seconds you would need for that process to occur, right? So the more accurate the measurement gets, again, the more refined our experiments get, and then we can learn more and more about things. So you guys may have heard that if we wanted to measure the smallest thing in the universe, right? If we wanted to measure fundamental building blocks of the universe, which we don't know what they are yet, then we would need a machine that's about as big as the universe, right? So this is kind of like we're going back and forth between designing better experiments and then measuring more accurate quantities. But to do that, we generally need more and more sophisticated machinery for that. And then a kilogram used to be defined as the weight of 1 liter of water. But now, based off of one of the famous quantum mechanics of the 1920s, a guy named Planck, he came up with an equation for the energy of light. And using these other measurements, meters and seconds, we can define a kilogram based off of a combination of those fundamental quantities and a constant, a universal constant that he looked at. And so we'll become familiar with that equation too. All right, so that's how we define these standardized units. And so then from the standardized units, we can have derived units, which I mentioned, right? So these are combinations of the standardized units, right? So some common ones are volume. The standardized unit is a meter cubed. Right, so the meter is the actual unit. That's an SI unit, and we cube that unit to then get a volume. And we can think of that as going through different dimensions, right? So if you're in 1 dimension, you're on a line. If you're in 2 dimensions, you're on a plane, right? So that's meters squared. And then to get 3 dimensions, we need 3 different length directions. And another one that we'll become more familiar with is density. And so density is mass per volume, usually, so kilogram per liter. Usually you see it as a gram per centimeter cubed, which is what grams per cc is there. Right, so these are also derived units. Some other common ones is force, which is, so sometimes we use these brackets. This means units of. Right, so if I'm ever writing something and I put these brackets around it, it'll get confusing once we get to concentrations because they have the same notation, but those brackets can mean units of. So the units of force are newtons, and what a newton is defined as a kilogram meter per second squared. All right, so there's another derived unit that we have there. And there's tons and tons of derived units that come from the standardized units. And these become important because, again, oftentimes when we're looking at different experiments or calculations we need to do, we have to go from one unit system to another. Or this is a really good way to check our work to make sure we're on the right track, right? Let's say you're solving for a density or something, and then you have units of time in there somehow. You say, okay, well, I multiplied by something that I didn't need to, or something didn't cancel out that I needed to cancel out. Right, so units are a good way. Good way to check work. So these are the different units that we're going to be dealing with. And units kind of go hand in hand with measurements. All right, measurements, kind of boil down to 2 different types of numbers. Right, so in measurements, we'll have 2 different types of numbers. We have counted or defined numbers, and these are going to have no uncertainty or error, right? So this is like a counting number, like 1, 2, 3. If you have 3 apples, for example, that is an exact number. There's no uncertainty in that. Measured numbers are always going to have uncertainty in them. right? And so because whenever we measure something, it always gets to a point where we have to estimate something. We have to estimate some value, right? So if you think about whenever you measure something in a ruler, you know, even if it lands exactly on one of the ticks on a ruler, you're still estimating that, you know, that decimal place is going to be 0. I'll talk about that more in a second, what I mean. But, or if it lands in between 2 tick marks, you kind of have to estimate how far it is between 2 tick marks on a ruler. And that's because every instrument has an inherent error in its design, right? You can only be up to a certain accuracy. There's no instrument that's infinitely accurate. And so this has instrument error. You know, people have spent a lot of time, you know, even fields like calculus come into play when we talk about how does error propagate through specific measurements. So if you find yourself very detail-oriented and you're looking for a career in chemistry, and one that can be pretty lucrative is if you want to become an analytical chemist, right? So these are people that design instrumentations and work on minimizing error, or if they do have a certain amount of error, which everything does, they can determine how error propagates through these different measurements that people are taking. And so analytical chemistry is the field that falls under, right? Because chemistry has many different sub-majors, you could say, in chemistry. In analytics is just looking at how does error propagate through chemical measurements. Okay. So let's take a look at, if we have 2 different rulers here, right? What is the error in the measurements that we're looking at? So we see we're measuring whatever this red piece of tape is, and on the top where it looks like we're dealing with centimeters, and on the bottom we're also dealing with centimeters, right? Both of these have a different level of precision in these measurements, right? So each of these, each ruler has a different level of precision. When you guys are working in the lab today, you'll see or get more practice doing this, right? Because on the top ruler, we have each centimeter, for example, is measured and calibrated for up to a single centimeter, but then there's 10 tick marks in between each centimeter. So that means that something like 4.1 is accurate on that ruler because you actually have a tick mark that's calibrated to that distance. On the bottom ruler, though, we only have each centimeter is calibrated to. That's the maximum accuracy that you can have certainty in, is that it's at least, for example, for the red tape here, it's at least 8 centimeters, right? Because there's no tick marks in between each individual centimeter in this case. And so what does that mean? That means when we're taking a measurement, we need to include the correct, I'm going to finish this up here, number of decimals. And we need to include the correct number of decimals to reflect the accuracy of whatever that measurement is. And so what you do is you always go to the estimated digit. You always include every digit to the estimated digit. So we always include to the estimated digit. And let's use the bottom as an example here. Right, so because we know this ruler is only calibrated to, the ones place in centimeters here, that means that whenever a measurement lies in between these tick marks, we have to estimate how far it is there, right? So that's what I mean when I say the estimated digit, right? Because we say, okay, well, this is somewhere between 8 and 9. I don't know, looks like somewhere between 6 and 7 there, right? So that means we know it's at least 8 because that's certain. How do we know it's certain? Well, the red tape goes past 8 and it doesn't reach 9. So it's at least 8 centimeters. Then we estimate whatever's left over here. If it was here, then we would know it's at least 7 centimeters. Then you have to include one more digit, which would be the estimated digit. Here, we know that it's calibrated to the 10th of a centimeter, right? Because we know that it's at least 8, but then we know it's at least 1, 2, 3, 4, 5, 6, past 6.6 or 6 tick marks in between 8 and 9 there, right? And because we know that it's past this line, it lies somewhere in between these 2 tick marks, so we have to include that decimal place as the estimated digit there, right? So you always include up until the estimated digit. So that's why up here we have to include 6.5. You know, it's kind of hard to see, and when the tick marks get really close together, it's gonna be really hard to see. But you still have to include that digit because that's where the uncertainty in the measurement is, right? So the uncertainty here is in the hundredths place, in the decimal place, and here the uncertainty is in the tenths place. And so what does that mean? That means that this is all determined by the specific instrument. All right, so that's inherent to whatever instrument it is that you're looking at. Meaning you have 2 different rulers, they both measure the same distances, centimeters here, but one is more accurate than the other. And whenever you're doing a measurement, like weighing something, taking the temperature, some thermometers are more accurate than other thermometers. So this is determined by the specific instrument. And so I know right now with the ruler, it might seem a little simple, but once we actually take measurements in the lab, you see that, okay, the estimated digit really does depend, because you guys are all gonna have different glasswares, and sometimes you have different number of tick marks on each glassware. And so this also, the last thing I'll leave here, a big star right here, is that all estimated digits are significant. All right, and on the next slide, we'll talk a little bit about what that means. Has anyone heard of significant figures before? No? Okay. Significant figures is basically designed so that, we don't ask, well, how many decimal places do I need to count when I calculate something? When I multiply two numbers together, how do I know that I don't include all 11 decimal places? Well, based off the certainty and the uncertainty in whatever measurement you're taking, that'll tell you how many decimal places you should be allowed to carry through these operations. All right, any questions on this? Okay, so that leads us then to significant figures, right? And so significant figures are going to be related to the uncertainty or the certainty in a measurement that you take, right? And so these are rules for how many decimal places do we keep and how certain or uncertain are we in that number, right? So the estimated digit here is the uncertain number, right? That's the one number that we're not certain to. That's the number that has potential error in it. And so all non-zero digits are going to be significant. So if I put purple here, that means that this digit, and this digit are all going to be significant digits. And then all trailing zeros are considered significant. What do I mean by trailing zeros? Well, a trailing zero is going to be any zero that comes after a decimal place and after a significant non-zero digit. All right, so this is after a decimal place. Or decimal, sorry, I should say, not decimal place. So that means that these two zeros here are significant. Why? Because it's after a decimal place. Here's our decimal place, and these come after the last non-zero significant digit. Then we have, let me put a little here, that's for the trailing zeros. Then we have sandwich zeros, before or after a decimal place. This should be significant, not significant. So sandwich zeros, if we have any zeros in between significant digits, those zeros become significant. So that means these zeros right here are significant. Why? Because we have a non-zero digit here, non-zero digit here. So any zeros in between those have to be significant. And then the last one, I'm going to add a not here. These are going to be leading zeros after a decimal place or before are significant. So that would be these zeros right here. So what that's saying is that those zeros right there don't contain any information about the number or measurement or the accuracy of the experiment. And the reason those aren't significant is because if you have a number like 400 and you put 5 zeros in front of it, the number is still 400. It doesn't change the number in any significant way. And one rule that I'll put here is that in scientific notation, all significant figures are in the coefficient. I just remember last time we were writing large or small numbers, all of that information is carried in the coefficient. So for example, this number here, how many places would we move the decimal place to convert this into scientific notation? 3, right? Because we're moving it to the right. Be 1, 2, 3. That puts our number between 1 and 10, right? And so if we move it to the right 3 places, what should our exponent be? It should be negative because it's going to the right, and then it should be negative 3, right? So this is going to be 4.004500 times 10 to the minus 3. We still include those last 2 zeros, again, because they're trailing zeros after the decimal place. But all the significant digits are contained in this, the coefficient within scientific notation. And this kind of follows from what we talked about last time because we said the coefficient contains all the information about the identity, the personality of the number, and the exponent just tells us the relative size, how big or small this number is going to be. Any questions on that? No? All right. All right, so here we have some examples. So why don't you guys determine, or spend 3 minutes or so, determine the number of significant figures in each of these numbers here, right? Each of them is given a unit as well. When we're dealing with chemistry, especially if it's not a counting number, units are always important or else the number doesn't mean anything. Your question too, Vanessa? Does that make sense? Yeah, so for this one, right, These are two significant digits. These are not significant because trailing before a decimal. Right, so this one has two significant figures, right? So SF, significant figures. And depending on your instructor, usually if you continue in chemistry, they'll be more or less lenient about, keeping track of sig figs. For this class, since it's intro class, we'll, make a point of focusing on it a little bit just so you guys are familiar with it in the future. But in general, it's kind of instructor dependent how much sig figs you're actually going to deal with, right? Some professors will just say just to round to a certain number of decimal places. Okay, what about 0.006? How many sig figs does that have? This number right there. One sig fig, right? It's just this one right here. These are leading zeros, right? You can put 0, 0, 0, a million zeros in front of the number 1, but it still is the number 1, right? So they only have one sig fig here. What about 93.500? It should be 5, right? So we have 3 non-zero digits, right? So those are non-zero, which means they're always significant. Any non-zero digit is significant. And then what about these two right here? How does that different from these zeros, these trailing zeros here? What makes these trailing zeros? They're after the decimal place, right? So these are trailing after the decimal. My handwriting is actually terrible today. After the decimal place, which means they're significant. All right, so this is going to have 5 significant figures. What about 461? 3, right? Because those are all non-zero digits, right? So this is 3 sig figs. They're all non-zero digits, so they're all significant there. What about 1,025? 4. So why is that 0 significant? Sandwich 0, right? Sandwiched, which means it's significant. So there's 4 significant figures. And what about 0.705 milliliters? 3, right? So this 0 here, why is that a significant 0? Sandwich. And why is this one not significant? It's a leading 0, right? Leading, not significant. And then sandwiched means it is significant. So this is going to have 3 significant figures. Right. And so for this number, how many digits do we need to include in if we wrote it in scientific notation? 2, right? Because remember, in scientific notation, the coefficient always has the number of sig figs in the number itself, right? So that's another reason why scientific notation is usually a little bit easier to understand. Instead of keeping track of all these leading zeros here and saying, okay, well that's not significant. If this was in scientific notation, it would just be 6 times 10 to the minus 3. You only have one sig fig there. All right, so sometimes it's easier to do all our calculations in scientific notation, also for keeping track of significant figures. All right, any questions on that? All right, so again, significant figures are related again to the uncertainty in the number, and how many digits do we include to make sure that we have the most accurate number possible. All right, so here we also have to think about rounding, right? So if we have an answer for a calculation, like this. You plug this in your calculator, you get something like that, and you know that you're only supposed to have 3 sig figs in your answer. Right? You're gonna have to round it to account for the correct number of sig figs. Right? So we're gonna use a basic rounding rule here. Depending on if, there's different rounding rules, there's usually only 2. We're gonna use the simple one, or if it's less than 5, the digit is dropped. If it's greater than or equal to 5, then the digit is increased by 1, and then the non-significant digits are left after that. So another one you might see is that because if it's exactly equal to 5, you do sometimes round up and sometimes round down if the digit is even or odd, right? So that adds like flipping a coin a little bit. Like if it's exactly in between the two numbers, then sometimes you round up, sometimes you round down. But we're gonna keep to these rules for rounding here. Right, so this is a question kind of posed a little bit differently than just asking for the number of sig figs, right? You're given an answer, so this is your answer, and you need to correct it for the correct number of sig figs, right? So for the first one, we want to round it to 3 sig figs. So how many digits do I need to include for 3 sig figs? 3, right? So that's straightforward, right? We need to include 3 digits here. So when we're rounding it, we then look to the digit before the last significant digit. If it's less than or less than 5, we just drop the sig figs, keep the number the same. And if it's greater than or equal to 5, we increase the last significant digit by 1. So do we change anything here? Right, so 3 is less than 5. So our number is going to be 8.42. And what about, actually I'll change the color here to red. If we have 2 significant figures, right, and we just include 2 digits, so you have 8.4, we look at 2, is that going to be less than, equal to, or greater than 5? Less than, right? So 2 is less than 5, so we get 8.4, our answer rounded to 3 sig figs and 2 sig figs. Right, so why don't you guys do the last 2? We'll do that, and then we'll take a 5 to 6 minute break. We'll come back and we'll take attendance and then continue. So what is 14.780 rounded to 3 sig figs? 14.8. Yep, 14.8, right? We keep 3 digits. The 8 is larger or equal to 5, so that means that we have to round the 7 up to an 8 there, right? So this one, 7 goes to 8 because we're rounding up. And what about to 2 significant figures? Just 15, right? So this will just be 15. What about 3,256 to 3 sig figs? 3, 2, 6. And then do we have to include anything else? A 0, right? When we're rounding to sig figs, we're still keeping the number the same magnitude, right? So if we don't include that 0 there, then we go from a number that's like 3,000 to a number that's 300, right? So the number doesn't change at all in the magnitude, right? You still have to always make sure, and that's something I see a lot, is that when you just drop the digits or you get rid of them, a lot of people, like after the decimal place, you just get rid of them, right? Because they're trailing zeros after decimal place. But before the decimal place, if you don't include that 0, that means you've effectively divided it by 10, right? So the number needs to be the same magnitude, the same relative size. So one way to remember this is, money. Let's say you're rounding change or something, someone's giving you money back. If you were rounding your own money and you had $3,256 and you're rounding it to $326, I think you'd be pretty upset if you only got $300 back, right? So think about in terms of money, you always want to keep the number the same magnitude. I guess if you get it wrong the other way and you give yourself $3 million back, that'd be good too. But whenever we're dropping digits, we have to make sure that we're keeping the number the same magnitude. Okay, and what about to 2 sig figs? Yep, 3,300. Right, and both of these zeros, they don't add to the number of sig figs. Why? why do both of these zeros here, or all three of these zeros, not add to sig figs? Yep, they're trailing zeros before the decimal place, right? Trailing zeros. Before the decimal means not a significant figure. Okay. All right, let's take like a 5-minute break. When we come back, we're going to start talking about rules for doing calculations with sig figs. How do sig figs carry through when we add, multiply, subtract, and divide? So we're talking about rounding numbers here. So next we're going to talk about calculations and how do significant figures carry through calculations, right? So whenever you're doing a calculation, you keep in mind that the result can't be more accurate than your least accurate measurement, right? So any measurement and then, something you calculate, like for example, today you calculate density, right? That can only be as accurate as your least accurate measurement. That puts a limit on how accurate your results can be, right? So this has to be the least precise or the least accurate measurement that determines the result. So the rules when we're doing multiplication or division is that the answer has the same number of significant figures as the number with the least. All right, so whenever you're multiplying or dividing, you count the sig figs of each of the numbers in your expression, and whichever one has the least is going to give you the number of sig figs in your answer. All right, so what does that mean? So for example, if we have 5.5 times 2, right, if you were to calculate this, that gives you 11, right? And how many sig figs are in 5.5? 2 sig figs. And in 2, 1 sig fig. So how many sig figs should our final answer have? 1, right? Because whenever we are multiplying or dividing, whichever one has the least number of sig figs gives us the number of sig figs in our final answer. So 1.1, right, that means that this is our last significant digit. We either round it up or round it down, or we keep it, round it up or we keep it the same. And so here, what do? Right, is this number larger, less than, or equal to 5? Less than, right? So this gets rounded to 10. Because we need only 1 sig fig in the final answer. All right, so whenever we're multiplying or dividing things, whichever number has the least number of sig figs determines the number of sig figs of our final answer. Summer?
Can you give another example?
Oh yeah, we'll go through another example. We have a couple to go through here, but we'll talk about. I'll give you the rule for addition and subtraction, and then we'll go through plenty of examples for this. All right, and then for addition and subtraction, the answer has the same precision as your least precise number. Whenever you're adding and subtracting, it isn't related to the number of sig figs in what you're adding and subtracting. It's related to the precision of that number. Another way of phrasing this is, change the color, the smallest number of decimals. Not all numbers have decimals, but whichever number is your least precise number, that's how precise your answer is going to be. And this is usually easier to see when you kind of add things up on top of each other by lining up the decimal place. So if we have 5.323 plus 2.10, this number is the more accurate number. How do we know it's more accurate? Well, because it has more decimal places, right? So this has a significant digit all the way to the thousandths place, right? This only goes to the hundredths place, which means that when we add these together, it can only be as precise as our least precise number. So this will give us 7.42. In this case, it just happens that it kind of works out that this only has 3 sig figs and we have an answer with 3 sig figs. But a lot of times the number of sig figs of your final answer is uncorrelated to the sig figs of what you're adding together. Right, because we're not thinking about sig figs of what we're adding and subtracting, we're thinking about the precision of those numbers. And again, this is always easiest if you stack the numbers when you're adding or subtracting them. When you multiply, again, you're just taking, your answer just has the lowest, or the same number of sig figs as your number with the least number of sig figs. Okay, and we'll go through some examples just to kind of hammer that in. All right, so here we have 3 numbers multiplied to each other, right? And so you multiply these in, you plug it into your calculator, and you get 23.4225, right? So what we need to keep track of when we're multiplying and dividing is what? What's the first step that we should do here?
Parentheses.
We have the parentheses, right? So we have each of these numbers in the parentheses. When we put them next to each other, that means they're all going to be multiplied to each other, right? There's 3 parentheses here. So this is multiplication or division, right? What was the rule for multiplication or division?
It's gotta have the same number of significant figures as the smallest.
Yep, it has to have the same number of sig figs as the number with the least number of sig figs. So a good place to start for this is just to get the number of sig figs for each of the numbers here, right? Find number of significant figures for each number being multiplied. Right, so that just means for each number in these parentheses here, we're just going to determine the number of sig figs. Right, so 9.2 is how many sig figs? 2 sig figs, right? 2 sig figs. 6.80 has how many sig figs? This is a trailing 0 after the decimal place, right? So this is trailing after decimal. That means that it is significant. So that's going to be 3 sig figs for that, right? So I know the zeros can be tricky sometimes. And what about 0.3744? 4, right? Because that's a leading 0, so that's not a significant 0. So this is going to be 4 sig figs. Right, so we have 2 sig figs times 4 sig figs times 3 sig figs. How many sig figs should our final answer have? 2, right? Because this is the smallest number of sig figs. Significant figures, which means that this needs 2 significant figures. Right? And so 2 significant figures means we need how many digits? 2. Right, so that's our last, the 3 is our last significant digit. We have to round the answer accordingly. So what do we do to the number? Do we change the 3 at all? No, because 4 is less than 5, right? So we keep that number the same. So that means that we just drop the rest of these numbers, and our final answer should be 23. Correct significant figures. All right, so whenever we're multiplying or dividing, the important thing is just to keep track of the number of sig figs of each of the numbers, and whatever has the lowest number of sig figs, that's how many sig figs your final answer is going to have. All right, so let's do another example. Let's do 15.320 times 0.23 divided by 6.89. So if you see if you guys can come up with rounded answer. And again, the first step was to determine significant figures of each number in the expression. When I say number in the expression, it just means everything that's in this fraction here, the number of sig figs of each term in the parentheses. Okay, how many sig figs are in 15.320? 5 sig figs, right? That 0 is significant at the end because trailing 0 after the decimal place, right? 0.23, 2 sig figs, right? That 0 is insignificant because, yep, it's a leading 0, right? Adding 0 in front of a number doesn't add any information to that number. And then 6.89 is 3 sig figs, right? So if there's 3, 2, and 5, how many sig figs should our answer have? 2, right? So we plug all this into our calculator, we get a number like 0.51140,783 and a bunch of numbers after that. We know we only need 2 sig figs, right? So we're going to round it to the hundredths place here. 1 is less than, equal to, or greater than 5. Less than, so that means that we keep the number the same, right? So that's our final answer, rounded to 2 sig figs. All right, any questions on that? Okay.
So why did we skip the division?
We still kept the division. How do you mean when we skipped the division here?
For the final answer, because for mine, like, I did the multiplication at the top, and then once I did that, I divided it by the denominator.
Yeah, so even if you were to do that, right, so if you multiply at the top, you would get, what's the number? 0.2, so it's like divided by 5, you get like 5 or something, right? So you get like 5. Then you have, if you want, you can do it that way, you can do it sequentially. You multiply 5 sig figs by 2 sig figs, how many sig figs should you get? In just the numerator there. If you have 5 and 2. 2, right? Then you have to round that to 2 sig figs. And then if you did the division of 2 sig figs divided by 3 sig figs, right? Your final answer should have how many sig figs? 2 again, right? So the reason that I kind of did it all in one step is because when you're multiplying and dividing, it doesn't matter what order that you do this stuff in, your final answer is always going to have the least number of sig figs in the entire expression. Only if it's only division and multiplication together. Did I answer your question correctly? Or did I miss this? Did I miss calculating this?
Because like the 0.1 that you got for the final answer, is that just from multiplying the top half? Because like what I got is like completely different. It's because what I did was I did the 15.3 and I times 0.23. Once I got that answer, then I divided at the end of that, and then that's how I got 17.75.
So when I did the same thing. So when I did 15.320 times 0.23, that's like dividing it roughly by 5, which should give you an answer around 3, right? And it might be just a calculator mistake, right? So that's like dividing by 5, that should give you like 3 something, divided by 6, which is a larger number, that's about like half of 6, is how I'm just doing the relative orders in my head. But let me see, so you're saying you did 15,320 times 0.23, right? And if I plug that in, 15.320 times 0.23, I get 3.5236.
Oh, wait, I'm tripping, yo. So I forgot to put the decimal.
That's what it sounded like that there was probably a decimal place that got mixed around there, right? So in my head, I was like, okay, well, 0.2 is like dividing by 5. So that's why I said, okay, that's gonna be a small number divided by something larger, so it should be less than 1, yeah. Ultimately, you know, if you did that on a quiz or something, that's just a calculator error, right? So the important thing that a question like this is testing is, what is the actual number of sig figs? So let's say you did put 17, you got 17 or whatever, and then you still had 2 sig figs, that's the majority of the credit for the, generally when I'm looking at questions, you know, some of the numbers aren't perfect or whatever, if the thought process is important for what the question is asking, that's the most important thing. Sam?
You should round at the end, right? Like as the last step.
I generally round at the end, but you know, there will be some calculations in the future that you might do where you have multiplication and then addition after, and when you do those things, you have to do them kind of sequentially. Here, like the reason that I just did it at the end is because when you multiply and divide, it doesn't matter what order you do it in, right? If it doesn't matter what order you do it in, like what we said, multiply the numerator, 5 sig figs, 2 sig figs, 2 sig figs in the numerator is what's left over. 2 sig figs divided by 3 sig figs, we still end with 2 sig figs, right? So the same answer is gonna have the same number of sig figs no matter what. If you add in other operations like addition, subtraction, there is an order of operation that you generally have to do first, but. Summer?
When you rounded in this example, are you looking at the first or second one? Is it because you skipped the 0?
Oh, so when I'm rounding it, so I'm looking, so what I underlined in blue, I know I have to keep those 2 digits, right? To have 2 sig figs in my answer. So this right here, that's a good question. This is the rounding digit, which means that's the digit I'm looking at to determine if I have to change this 1 to a 2 or leave it the same.
Okay, that's because you skipped the leading 0, right?
Yeah, that's because I skipped the leading 0. Why did I skip the leading 0? Because it doesn't change the number of significant figures, right? I'm only going to where the sig figs are in the problem. Good question. Okay. Any other questions? This is one of those things when we go over, it's like, okay, yeah, it makes sense or whatever, and then, you know, when it comes to practice, it's just gonna take practice to get used to. All right, so let's do an example of adding and subtracting them. So if we add 83.5 and 23.28, the first step in adding should be to line up the numbers according to the decimal place. And what I mean when I say that is that if I have plus the first number and the second number, I just want the decimal place to be in the same spot, right? So we have 83.5 and 23.28 when we add those. And again, even if you can, you know, generally do the calculation by going through, I forgot what that method is called, where you know, carrying numbers and stuff like that. Even when you're adding and subtracting, I recommend lining it up like that to know where your cutoff is gonna be, and then just plug it into a calculator, because you're less prone to error to doing it that way. All right, so we line up the numbers. I put 83.5. It doesn't necessarily matter which order you line them up in, unless you're subtracting, because then you can get negative numbers. 23.28. Right, so what was the rule for addition and subtraction again?
Keep the lowest amount of decimal.
Keep the lowest amount of decimal places, right? We're gonna have the same precision as our least precise number, right? That's a kind of technical way of saying it. easier way to remember is whatever has the lowest number of decimal places, that's the number that we're gonna match for our answer here. Right, so which number has the lowest number of decimal places? 83.5, right? This is our least precise number. And what we can do is we draw a line to the right of our last significant digit in our least precise number. So that's just a wordy way of saying I'm just going to draw a dotted line right here. And where that cutoff is, with the decimal place still right here, that's going to be the cutoff for our final answer here. All right, so again, like I said, you can go through the mechanics of adding this together, but I think it's easier just to plug it into the calculator, and then you have, you're less error prone that way. So what I do is I get 106.78. Right, so that means I'm keeping everything to the left of this line right here, right? And I do have to do some rounding here. So what should the final answer be? 107.8. Right? This number is our last significant digit, which means that this 8 right here is our rounding digit. I'll make a note of that. This is the rounding digit. Right? It's greater than 5, so 7 goes to 8. Greater than 5, 7 goes to 8. So this is what I mean when I said that the number of final sig figs in your answer isn't necessarily correlated to the number of sig figs of each of what you're adding or subtracting, right? This has 4 sig figs, this has 3 sig figs, and we end with 4 sig figs. Right, so in this case, we actually have more significant figures than the number with the least significant figures, right? Because when we're adding and subtraction, we care about precision of the number, not the number of sig figs of the number. Oops. Okay, any questions on it? Jordan? Doug? Oh, sorry, I meant to do 106.8. Yeah, sorry, rounded one extra digit over. Thank you. Is that your question too?
No, I think I missed it. Why did you cancel out the 7? Why is it 106.8?
So I didn't cancel out the 7. What happened is that this is my last significant digit, and I have to round it accordingly, right? So this is the number I get in my calculator. I have to round it accordingly. And so what that means is that I have to look at the digit to the right. Is it less than 5 or greater than or equal to 5? If it's less than 5, this number stays the same. If it's greater than or equal to 5, then I have to bump that number up 1, right? So whenever we get rid of numbers, we always have to round the number accordingly. So for example, if it was 106.73, then I would just leave that answer as is. Good question.
We are rounding to 3 sig figs, right?
So we don't have to round to any number of sig figs in the case of addition and subtraction, because the rule is we just have to stay as precise as our least precise number, right? So the number of final sig figs doesn't correlate to the number of sig figs of what we're adding and subtracting. When we're multiplying and dividing, then we have to round it to the least number of sig figs. With addition and subtraction, once we find the cutoff for the least precise number, that means that gives us our final answer. So technically, let's say these were, even bigger numbers, and let's say you had 2 sig figs and 3 sig figs here, you can technically end up with a number with like 5 sig figs if they just happen to line up that way. All that matters is that you're not giving an answer that's more precise than your least precise number, right? So another way we can think of this is we have 83.5 is only accurate to this digit here. right? That means if this measurement is only accurate to that and we add it to another measurement that's more accurate, then the final answer can't be more accurate than whatever was the least accurate number. Right, that sets a limit on what our final answer can be. Good question. All right, so we only have about 3 minutes left. So I'll give you guys one to kind of think about. And so here we have 3 numbers. The strategy is still going to be the same here. 5.08 plus 16.2 plus 13.48. So again, the first step is line up numbers by the decimal place. And if you're confused on what I mean by that, don't hesitate to ask. It's just that you want the decimal place to be in the same spot when you line up the numbers. That way you can, gives you a good visual cue for how precise each number is. They're all lined up. Since we're adding, it doesn't matter what order we add in. 5.008, 16.2, 13.48. We add those all up. What was the second step? Yep, we find the least precise number and draw a line to the right of last significant digit. Right, so what's the least precise number here? 16.2, right? So then we're going to draw a line to the right of the least significant digit, which is this 2 right here, and that's going to give us the precision of our answer. So we go dash line up like that, and then we're going to have the decimal place in the same spot. I'm going to plug everything into the calculator. And we get 34.688. Everything to the left we keep, everything to the right we drop. So what should our final answer be? 34.7, right? 34.7. Why? Because we had to round when we drop these numbers here, or these digits here. 8 is larger than or equal to 5, so 6 has to go up to 7. All right, so, oops. This is our rounding digit. 8 is greater than or equal to 5, which means 6 goes to 7. All right. And again, you guys can do all the math of adding this all up, but it's easy to kind of make mistakes when you're adding everything together. So I think it's good just to set it up so you know where to cut off the decimal place, and then you just plug it into the calculator. You're less prone to error there. Okay, so we'll leave it